In a surprising revelation, the James Webb Space Telescope just announced the first ever real image before the Big Bang, challenging cosmic convictions. This groundbreaking discovery raises questions about the pre-Big Bang existence and its impact on our understanding of the cosmos. Do you know about the Big Bang? No, not the hit TV show, but the scientific theory about the birth of the universe. Recently, the James Webb Space Telescope gave us some mind-boggling findings about what might have occurred before the Big Bang. But let's take a step back and try to understand what the Big Bang itself was and how it shaped the universe we live in today. Let's imagine the beginning of everything as a super hot, incredibly dense, and tiny speck of energy and matter. This is how the universe began, according to the Big Bang theory. Picture this point rapidly swelling up, getting bigger and bigger while cooling down. This expansion and subsequent cooling set the stage for everything we see in the universe today: the atoms, stars, galaxies, and all other structures. And not only that, the James Webb Space Telescope just announced the first ever real image before the Big Bang. What backs this Big Bang theory? There are several pieces of compelling evidence, one of which is Hubble's law. This law notes that galaxies far away from us are moving further away and doing so increasingly faster. This suggests that the universe was once a much smaller, compact place and has been growing steadily ever since. From calculating this rate of expansion, scientists have concluded that the universe is around 13.8 billion years old. Another crucial piece of the puzzle is the cosmic microwave background, or CMB for short. This is a sort of radiation residue left from the fiery beginnings of the universe. It blankets the entire sky, creating a subtle glow. Tiny changes in the temperature of the CMB hint at the density differences in the early universe's plasma. It was not until 380,000 years after the Big Bang that atoms could form, allowing light to travel freely, as indicated by the CMB. Further evidence supporting the Big Bang comes from examining the earliest elements present in the universe. Scientists have found that the universe is largely made up of hydrogen, helium, and a handful of lighter elements like lithium, beryllium, and boron. These elements were created through nuclear fusion in the minutes following the Big Bang, when the universe was hot and dense enough for atomic nuclei to form. The predicted quantities of these elements by Big Bang nucleosynthesis, a theory explaining the creation of matter in the early universe, match what we observe. The observation of galaxies also informs our understanding of the universe. Galaxies differ in appearance, age, and chemical composition based on location and history. Rather than being randomly spread out, galaxies cluster together, forming superclusters linked by thin strands of matter. This structure implies that matter first started to clump together due to gravity, leading to the formation of the first stars and galaxies. It's also observed that galaxies farther from us are older than the ones closer. Now let's circle back to the original question. What happened before the Big Bang? This is a question that both intrigues and puzzles cosmologists. The Big Bang theory tells us that the universe started from an incredibly dense, hot state before expanding and cooling. But what led to this state, and why it existed, is not explained. Scientists have proposed several theories about what could have been before the Big Bang. For instance, the Big Bounce suggests an alternate universe existed before ours, which collapsed into a singularity and then sprung back into existence. This cycle might have been repeating indefinitely. Another theory, the Big Spike, proposes that quantum processes could have sparked the Big Bang. Just like gravity, space could also have dimensions. These are just a few of the fascinating theories that strive to unravel the mysteries of our universe's origin. Do you know what the ekpyrotic scenario is? In this fascinating idea, our universe was born when two tiny layers of matter and energy known as brains crashed into each other. These brains live in an area with more dimensions than we usually think about. This collision triggered an explosive growth, or inflation, which smoothed out the early lumps and bumps of our universe. What's more, it could be that these brain collisions happen regularly, each time giving birth to a new universe. Another concept, known as the pre-Big Bang scenario, suggests that our universe transitioned from a state of low energy and high curvature to its present high energy, low curvature state. This shift sparked a period of superinflation that magnified tiny quantum fluctuations into the first seeds of the universe. This idea is supported by string theory, a theoretical model that aims to unify all the fundamental forces and particles of nature. But what if the Big Bang happened in a place without boundaries, where the size of the universe shrinks to nothing? This no-boundary idea suggests that the Big Bang of our universe was triggered by quantum fluctuations that popped out of nothingness. According to quantum physics, a wave function that includes all possible futures shapes the features and makeup of the universe. These theories don't necessarily cancel each other out. They might even complement one another. One of the key missions of the JWST is to uncover how a universe evolves. In its early observations, it has found a group of galaxies that formed just 650 million years after the Big Bang. In theory, the universe should follow a predictable pattern of growing complexity. In the earliest stages, the universe was almost perfect even during the Big Bang's hot phase. Everything was spread out evenly across space, with tiny variations in the overall pattern. These fluctuations, which are visible from medium to galaxy-sized scales, likely come from cosmic inflation, an event that came before the Big Bang and set the stage for it. Gravity has a strange effect on these fluctuations. While denser areas grow, less dense areas lose their matter and energy to their surroundings. Even though gravity can reach an infinite distance, the universe's expansion isn't influenced by gravity in the same way everywhere. The speed of light sets a limit on how fast gravity can spread, just like it sets a limit on how fast any other information can spread. It takes a set amount of time for nearby matter to be attracted to an area in space with more matter, but it takes at least 10 times longer, maybe even more, for matter 10 times further away to be drawn in. The bigger the cosmic scale, from clusters of stars to galaxies to groups and clusters of galaxies and beyond, the later gravity begins to pull things together. Once gravity has begun to affect a large area, a bound structure takes a long time to form. The matter being pulled away from the center of gravity has to slow down before gravity can bring everything together. There has to be a critical mass of extra density, defined as being 68% more than the average in that area. After that, the massive structure has to stop growing, do a 180-degree turn, and start to collapse. The result is a bound object, made up of separate pieces that come together to create a whole structure on a grand scale. The first stars and star clusters are created on smaller scales when gas, dust, atoms, and dark matter in molecular clouds collapse. While the usual collapse of these dense regions might take 200 to 250 million years, the collapse of regions with the most extreme initial conditions might only take 50 to 100 million years. So, from the tiniest fluctuations in the early universe to the grand structures we see today, it's all part of the complex evolution of the cosmos. Stars are like busy factories, churning out light, heat, and even wind as they form. This makes it difficult to say exactly what the first stars looked like. When galaxies, which are basically giant star collections, bumped into each other, they sometimes merged. This led to the creation of the first big galaxies in the universe. As early as 320 million years after the Big Bang, astronomers have found galaxies that were already growing old. The JWST has been able to observe these early galaxies in detail. Their stars are different from anything we've seen before. Finding these galaxies was one of the reasons the JWST was built, but scientists still hope it will discover even older stars and galaxies. Subscribe to the channel if you still not have yet. Even though a lot happens within galaxies like stars forming and dying, winds and radiation, all these events don't really change the size of galaxies. How galaxies group together depends mostly on three things: how fast the universe is expanding, how much extra matter was there at the beginning, and how quickly gravity gets stronger over time. Gravity is the main factor here, not what's happening inside the galaxies. Before the James Webb Space Telescope, astronomers found galaxy clusters by looking for many galaxies in the same part of the sky, moving at different speeds. These galaxies' movements and the X-rays they give off told us more about these clusters. Don't miss out on viewing this video on your screen, which showcases the most captivating images that scientists have been seeking for decades. This is a visual treat that beautifully illustrates the wonders of our universe.